Okay, so our next speaker is Kyriakos Georgiou. He's a research associate and PhD student at Bristol University. And he's probably got the best title of the day. Is your code as cool as expected? Kyriakos has an MSc in Internet Technologies with Security from the University of Bristol and BSc in Computer Science from the University of Cyprus. He has also worked on Compiler at Exmos and then at Paralant Limited. Since 2012, Kyriakos has been working as a research associate at the University of Bristol. His main research interests are WCET analysis, static code analysis, compiler optimizations, power consumption analysis, optimizations, and software testing. Thank you.
Thank you for the introduction, Mike, and thank you for the opportunity. So my presentation today is going to have a little different flavor from the rest of the presentations. And this question really goes to the software developers. So is their code as cool as expected? And my personal answer is that they don't have a clue. And what I'm trying to show today is what we consider the solution to this problem, which is energy transparency from hardware to software. So I'm going to put this into the context of the Internet of Things. So we see that Internet of Things is now no longer just on paper, but it's actually a reality. And the predictions say that by 2020, more than 15 billion small autonomous devices will be embedded on all kinds of objects. But the real challenge here is how are we going to power all these devices? So shall we plug them into a power network? I think this is impractical. What about batteries? Well, it's not cost efficient because they need replacement. And trust me, replacement costs more than the actual battery. And we end up with the solution of energy harvesting. So energy is scattered in the environment all over around us in the form of solar energy, thermal energy, mechanical vibration energy. And by harvesting this kind of energies, we can create electrical energy to power up our IoT devices. But there is a problem here. These technologies are not yet mature enough to produce the energy required budgets to power up the Internet of Things application. So there is a gap between what we can get out of it in terms of energy budgets and what we need to use. And to reach this gap, we need really to work from both directions. But what I'm going to concentrate today is from the Internet of Things hardware and software side. So what have we done to bridge this gap till now? From hardware design point of view, lower power has been a first-class design goal for more than a decade. But what about software? How we design energy-efficient software? How can we verify energy or power budgets for our software? And how can we support energy-aware decisions during development and runtime for embedded systems? My answer again is energy transparency. So ideally what we want is information of energy usage available for programs without executing them and at all levels of software, from machine code to higher level application code. And energy transparency is the key to enable a deeper understanding of how algorithms and coding impact on the energy consumption of a computation when executed on the hardware. So currently the only way to know the energy consumption of our software is either by physical energy measurements or simulation. But with physical energy measurements, we have the problem that you need special equipment or you need advanced hardware knowledge, which both of them are not easily accessible to every software developer. I mean, the technologies are picking up now by placing energy prompts on some embedded devices, but still there is some catch-up on that. And simulation-wise, it's too time-consuming most of the time. And another problem with these two approaches is that if you're trying to bound your energy consumption because you have a critical application that is running on limited or unreliable sources of energy, such as energy harvesting, then by measuring, it's almost impossible. Well, it's very difficult to get the bounds. So what we are proposing is energy consumption static analysis. An overview of this, how it will be integrated in the software and development lifecycle, is the developer will create his code, write his code, then he will annotate his code with, I want this function, for example, to run in this energy budget. Then it will take it through the analysis tools, which our main components is the energy estimation techniques and the software energy modeling. And then the analysis will return back to him, is your energy budget met or not? And also it will return hotspots of your code that are energy consuming. Then developer will take this into consideration, alter his code, pass it through the analysis iteratively as many times as he needs, until he gets the required energy budget and energy efficient code. So what are the main components of our analysis? We have the low-level analysis, which essentially are our energy models. Then we have the control flow analysis, which captures the dynamic behavior of the program. And then we have some computation techniques to estimate the energy consumption. For our case, we are using two techniques, the cost functions and implicit path enumeration technique. So let's have a quick look on the low-level analysis. Here is an example of an ECSA energy model for the XMOS X4 architecture. This is an ECSA-based characterization, energy characterization. The core is also multi-threaded, so our energy model is also multi-threaded. We capturing the energy consumption of the whole instruction set, and it's also voltage and frequency parameterized, which is quite nice if you want to do design space exploration using those two parameters. And here is just an example of how we are measuring the setup that we are monitoring the energy consumption of the core. Okay. And then you are ending up with something like this. So this is essentially our energy model. It's a heat map representing our energy model. And essentially it's the energy consumption of each instruction together with the inter-instruction effect. So if you take two instructions in the pipeline, how much is going to be the cost of running those two instructions? And as we can see, we can already see from our energy model that the energy consumption of different instructions varies significantly. And then we did the same for 32-bit data and 8-bit data. And we already get some transparency here because you can see that the 8-bit data is way more cooler than the 32-bit data. And now to the next component, control flow analysis. So the first level that we are applying our analysis is at the ECSA level of the architecture. So we have our energy model, the resource techniques applied to that level, and then we get our energy estimations. The first technique is cost functions, and I'm going to give you a brief example of how we are doing this using the factorial function. So firstly, you need to extract your cost relationship. So we say the cost of the factorial when the branch is taken is the cost of the condition and then the cost of the first return. And then the cost of the factorial when the branch is not taken is the cost of the condition and then the cost of the second return. And the cost of the second return is the multiplication together with the cost of the recursive code. And then we can substitute this cost with the actual energy required because through our ECSA energy model that we already construct. And then by passing these equations, the cost relations here, to a solve of the self-solver, we can essentially end up with something like this, which is a function describing the energy consumption of our code, parameterized to the input of the function. And when we apply this on a number of parameters, the green line is estimations, prediction that we get from our cost function, and the yellow line is the hardware measurements. So we can see that our predictions are pretty good. And then we apply this for a number of benchmarks. So the second technique that we are using is the implicit path enumeration technique, which is a very popular technique in worst-case execution time analysis. And what it tries to do is to express the search of the worst-case execution time as an integer linear programming problem where the execution time is to be maximized under some constraints on the execution count of the basic block. In our case, what we are doing, we are replacing the cost of timing with the cost of energy. And we are using exactly the same technique. Here is a brief example. Let's say you have some code, it's a JPEG PCD code. Then you need to construct your control flow graph. You need to annotate accordingly. Then you formulate your problem, the integer linear programming problem. You create your function, then you put some constraints on the control flow graph, you put some constraints on the loops, bounds, you pass that to a linear programming solver, and then you retrieve either the worst or best case bounds. So we currently see our analysis applied at the ECSA level where actually our energy model was built. But there are more software levels. 5 minutes, okay. Going up to the software stack, you're losing precision when you're applying your analysis, but you are actually more close to the source code. So we also apply our analysis to the LLVM-IR, intermediate representation of the LLVM compiler, by creating a mapping tool which creates a fine-grained mapping between the LLVM-IR code and the ECSA code. So by knowing which ECSA instructions correspond to which LLVM-IR instruction, then we can aggregate the cost and figure out the cost for the LLVM-IR instructions. So with this mapper tool, we were able to lift our ECSA model to the LLVM-IR, the energy model, and then we can apply the resource analysis also at the LLVM-IR code. And here are some of our results. So highlights here is that we are using also single-threaded and multi-threaded programs, 2, 4 threads, 7 threads. We have here the result from the simulation, applying the energy model, the result from the isostatic analysis, the results from the LLVM-IR analysis, and we can see that we are keeping everything between 8% of average error, and the LLVM-IR analysis is between is not far than more than 1% from the ECSA analysis. Here are some more results for matrix multiplication: 1 threads, 2 threads, 4 threads for different inputs, and we can see already from here that you can do some design space exploration to choose how many threads according to your program. Here is another case of results for the direct export division, which we get 2 flat bounds, and we can actually measure the worst case because we brute for the whole space. You can see that the worst case is actually very tight bound by our retrieval estimations. And here we have created a second version which is less balanced. We took out some optimizations, and we figured out that this is a very interesting property for cryptography, for side channel attacks, because when you bring the 2 bounds close, it means that you have less variation in your energy consumption, therefore you are revealing less information. And I'm going to leave you with some words from Steve Ferper from one of his recent interviews in the ACMQ, which he said, if you want an ultimate low power system, then you have to worry about energy usage at every level in the system design. And you have to get it right from the top to bottom, because any level at which you get it wrong is going to lose you perhaps an order of magnitude in terms of power efficiency. I think one of the hard questions is whether you can pass the responsibility for the software efficiency right back to the program. Do programmers really have any understanding of how much energy their output is? What you need in order to be able to work in this way at all is instrumentation that tells you that running this algorithm has this kind of energy cost and running that algorithm has that kind of energy cost. You need tools that give you feedback and tell you how good your decisions are. Currently, the tools don't give you that kind of feedback. Thank you very much.
Thank you, Kyriakos. Any questions for Kyriakos? Yeah.
Chris Cannon from Qualcomm. So in your modelling, I may misinterpret your slides, but it's very much based around total energy consumption for the algorithm. Are you taking execution time into account there as well? Because typically for IoT devices where the duty cycle is such that you want to power down the device, you power it up, you go to a Bluetooth 15.4 connection and power down as fast as possible. So I'm just wondering if the execution time is in the balance.
So you mean this model?
Any of the two strategies?
To be honest, on embedded system, the energy and power time is very close. So yes, in the model there is also time to energy. So the same techniques at the same time, you can use the same techniques to have the timing information, timing cost. So then you can, when you are having several threads and the energy consumption and the timing, you can do some design exploration to figure out what is the best setting. So yes, it is taken into account.
Okay, it's a good question. I know it's always a debate whether to do it fast and power down or just reduce the frequency and do it slowly. It's a good question.
This can help you answer the question.
Yeah, but there's the answer. So, any more questions for Kyriakos? Yeah, Chris?
So, this is Chris Brown from Arm in Cambridge. So, how much of the system do you need to model to get accurate results? I was thinking if your processor runs out of the local cache, you'll have a very different energy consumption if all the data is having to come from main memory. So,
well, yeah, that's the thing. What are you really targeting? Because if you have a critical application or if you have an Internet of Things application, are you going to put a cache in it? So this is mainly targeting predictive level architectures right now, like XMOS and Cortex-M series, which you don't have cache. You can have cache, but you don't have in these cases. But you can extend these techniques really by adopting more techniques from the worst-case execution time community, because there is a lot of work there done for caches and other stuff, which we didn't adopt yet because you need time to do this. But yes, there are techniques to take this into account. It always depends what kind of cache you have. So using LRU cache or which are more predictable, you get better chances of figuring out the time and the energy consumption better.
I'm just thinking a lot of software doesn't know exactly what hardware it's going to get run on. So
yes, there are techniques that you can bound. So if you do abstract interpretation, for example, you can figure out where you can have some read some cache and then or misses, and then you can take that into account. And your energy model can also have a different energy cost for these cases.
Okay. Okay, thanks. Thank you very much, Kyriakos. Thank you.